Granted that for many, math might be considered a foreboding science, I hope by the end of this presentation, many of your fears will be allayed. Today I'm going to discuss a problem called the classic conjecture. But I hope to do more than just solve this problem. I hope to stimulate some understanding of the fundamental thought processes that undergird all of problem solving. I hope to use some down-to-earth logic and hopefully demystify at least a portion of mathematics. Too often I feel a student may read or scrutinize a very beautiful, elegant proof in a math text or journal, but be left with the question, how in the world did the solver know to solve this problem in that way? How did he know to add x to both sides? And I found through my own study of the classic conjecture that the answer is that problem solvers rarely conceive of their solutions in well-defined, organized manners. In fact, often they use guesswork or trial and error. I have found that making a proof elegant strips it of exactly what makes it most useful. And what is that? That is the opportunity for the student to jump into the mind of the solver and walk through the solution as the solver did for the first time. Why is this important? Well, through the jumping into this problem, the student perhaps can pick up some of the tools that the problem solver used in order to solve this problem for the first time. And if he can do that, then perhaps he can apply those same techniques to a new and entirely different problem. This, I feel, is the magic and perhaps the point of mathematics. So let's get to it. This is the classic conjecture. And when looking at this, when we'll see a jumble of letters and characters and very few numbers, in fact, and be left with the question, what in the world is this? What does this all mean? Well, the first step to understanding any math problem and to solving any math problem is to understand what everything means. And so the key to this one, as I'm sure you'll notice, is that we have two polynomials, a p of x and a q of x, both nth degree polynomials. And the only difference between these two polynomials is that their coefficients are in reverse order. You'll notice that the a sub n here is transported to the bottom constant a sub n there, and so forth down the row. Okay, but what is this problem asking? It asks us to conjecture and prove a relationship between the roots of p of x and q of x. And then the student is left wondering, what in the world does that mean, and where do I go from there? Well, first place to start is to note that a root is at an x value where, when evaluated into a function, it equals 0. Okay, so now knowing this, where do we go? The key to this is through concrete examples, feeling out your environment. It's called the analysis. And the use of concrete examples is to get a sense of where the solution might lie. And so let's try one. Let's take a simple function for p of x, such as where n equals 1. We'd have p of x equal, let's say, x minus 5. And so this is what we would have. And we know that the roots of p of x equals x minus 5 would be simply where x equals 5. And we say, OK, that's fine. But what does this mean? Well, the key there lies in understanding what q of x, the related function, is. What does that equal? Q of x would therefore equal negative 5x plus 1. And notice that it's just the reversing of the coefficients. So let's take a look at what the graph of q of x might look like. And we'll note that the roots of q of x are 1/5. Now this is an interesting fact, because what we have done is taken a concrete example that we've just dreamed up. It could have been anything. And we compared their roots of p of x and q of x. And we noted that the roots of p of x are at 5, and the root of q of x is at 1/5. Now, if this is true, then we dig back into our mathematical library of knowledge, and we say, 5 and 1/5, we say, aha, they're reciprocals. But this isn't quite enough. For, of course, one example is never enough to prove a hypothesis. And therefore, we should try other examples, perhaps at roots equal to 0, or roots that are rational or irrational, or even complex. But for the sake of time, let's go out on a limb and see if we can't prove that the relationship between the roots of p of x and q of x aren't reciprocals. And so this is what our hypothesis would look like. Simply, it is a restatement of the problem, and then the roots of p of x and q of x would be reciprocals. Now, can we prove this? Okay, so this student says, fine, all the easy stuff is over with. We've done some concrete examples and we have a hypothesis, but we still have this monster to prove. How in the world does someone go about proving that the reciprocals, I mean the roots of p of x and q of x, are actually reciprocals? And the answer here is through a technique called box in, box out. Box in, box out is a way of organizing your thoughts. The box in is filled with what is given, what is known. And the box out, therefore, is filled with what you want to prove. The box in might be a starting point, everything that you know. And the box out would be your destination. If this were a journey, then the box in would be where you would start, and the box out would be where you would end up. And that path that you took would be your proof. And the magic of the box in, box out method is that if you can start at the box in and move to the box out, then you know that you have proven the problem. So let's see if we can't do that. So this might be what the box in looks like. Again, it is a statement of p of x, and therefore what the related q of x equation might look like. And so it's all that's given in the problem. Now, the box out is a little bit more complicated. It tells us what we want to prove. And to do this, we introduce a variable called r. R would stand for a root. And by definition, we know that if we plug in r to the polynomial p, then that equals 0. But what do we want to prove? Nothing less than the root of q being 1 over r. So 1 over r is plugged into the q polynomial, and wherever there was an x in the q polynomial, we put in 1 over r. And that's where we get this. So these two equations are simply restatements of the same thing in different forms. So this is what we want to prove. If we can move from this step to this step, in the box in to the box out, then we've proven it. Now the student says, fine, box in, box out, concrete examples, that's easy. But how in the world does someone prove this? We still are left with this problem. Now the answer to this is to very carefully compare the box in to the box out. And so we start with the box in, because that's a natural place to start. And we say, suppose that there's a root of p at x equals r. And then what does this mean? This simply means that if we plug in r into every place we have an x in the p equation, then this is what we would end up with. And we set this equal to 0 because that is the definition of a root. Now all this seems logical. But where do we go from here? We go to the box out, and we compare very carefully to see if there's actually a relationship. So we remember that the box out would look like this. And this is taken strictly from the Adler transparency. And then we say, is there a relationship between these two? Well, I had already mentioned before that we have an a sub n term here and an a sub n term here. We say, OK, we know that all the coefficients are in reverse order. And then you ask yourself, is there a way that we could go from what we know to what we want to prove? And we say, well, let's just look at a sub n. We have in the top line a sub n times r raised to the n. And in the bottom line, it just turns into an a sub n. Somehow, something has changed in there. And again, we reach back into our mathematical library of knowledge, and we say, is there a way to go from here to here? And we say the answer is by dividing by r raised to the n. But of course, we couldn't just divide by r raised to the n for this equation or this equation. We'd have to divide across the whole, every term. So if we divide by r raised to the n for every term, then we'll note for perhaps a sub 0, if we divide by r raised to the n, what do we get in the q of x equation? Simply a sub 0 over r raised to the n. We say, something is clicking here. We might have hit something. Because if we continue this process and see for each term in what we know, if we divide by r raised to the n, we'll see that we're actually reconstructing the q of x equation. So we asked ourselves, is there a relationship between the p of x and the q of x equations? And the answer was yes. And what we found was by dividing by r raised to the n, we could construct what we want to prove. Now we know that dividing by r raised to the n is perfectly legal, because if we divide by r raised to the n here, and we divide by r raised to the n here, 0 divided by r raised to the n will simply be 0. And so we get another equation, which happens to turn out to be this one. And we say, Eureka, we found it. But we're not quite done. A mathematician wouldn't quite be pleased with this. He'd have to see it in an elegant form. So let's see if we can't do that now. An elegant solution might look like this. And the beauty of the elegant solution is that we can now have 20/20 hindsight. We can look back and say, maybe there's a better way to solve this problem. Maybe a quicker way, a more clever way. And so how do we start out? We start out by resaying the problem. And then we say, let there be a root of p that we'll call r. And this is what we know about roots of p at r. Then we go on, and we say, now we jump to the box out. Instead of going from the box in towards the box out, we say q of 1 over r will equal this. And if we factor out a r raised to the negative n, which is actually the same thing as dividing by r raised to the n, then we'll end up with an expression right here, which is actually equal to p of r, which, of course, we know p of r equals 0. So it drops out, and we get q of 1 over r equaling 0. What does this mean? This means that we've proven that a root of p at r implies a root of q at 1 over r. Simply, we are done. We have proven that the root of p and q are reciprocals. Now it's time to take this one step further. We're not quite done yet, because we noticed through the solution of this proof that we've actually proven something more powerful than what the problem asked. And that was through concrete examples. But a mathematician might stand back and say, wait a minute, there's something wrong here. And that astute mathematician would be saying, what happens if there was a root at x equals 0? Now, if there was such a root, then that would mean that for q of x, the root would be a reciprocal of 0, which of course would be 1 over 0. But that doesn't quite make sense, because of course we know division by 0 is a no-no. So what does this all mean? We go back into the p of x equation and we say, if we plug in 0 into p of x, then what we will get is a sub 0 equaling 0. Because we'll notice that if p of 0 is plugged into here, then each place where there's an x term will drop out. And all we'll be left with is an a sub 0. Fine. So that means that a sub 0 would equal 0. We say, wait a minute. I read something before about a sub 0. And we look a little bit farther and we say, a sub 0 does not equal 0 was stated in the problem. And we say, aha, now I know why it was there. And again, things start clicking into place. But there's one more step that we can take in this, and that is to prove that this property that we found about functions p of x and q of x hold for something more than just the regular nth degree polynomial. In fact, this proof holds for such functions as this monstrosity. And what we find is that p, and therefore q, can be of any form as long as we have coefficients that are complex, exponents that can be either complex or an expression in terms of x, and that the number of roots of p will equal the number of roots of q. So what have we done here? We started with a problem that asked us to prove a relationship between roots. We used concrete examples to figure out if we might find some relationship. We found that relationship, and then we sought out to prove it. Finally, we proved it through the use of the box-in, box-out method of going from what we know to where we want to be. And then we took it one step further, past what the books say and anything that has ever been written about this problem, as far as I know. And we found that there's actually a very beautiful relationship between functions of p and q. And it holds in this manner. Thank you.